Today we're going to finish this chapter on the attenuation of sound. There'll be a problem set tomorrow, and then I'll send out a quiz. It won't be due until later on next week.
Class on Wednesday.
Excuse me?
Will we have a regular class on Wednesday?
Yeah, we start our material in the 10th chapter. But if you're traveling or something, you can always look at the video, right? Okay. Okay, so now finally we're at the point where we can understand the two mediums of interest here, mostly of interest, and that's air and water. So we'll start off with air. And what is air? Well, it's mainly, as you all know, it's mainly diatomic nitrogen and oxygen. However, there are traces of water molecules, H2O and CO2, and other molecules. So the way the results are presented here is not in terms of alpha, the absorption coefficient, but in terms of it might technically have a different name. It doesn't, it's not, people aren't strict about this. I think we might have called it the loss, I think KFCS might call it the loss factor. But what it is whatever words you want to put here, you just need to understand that it's in dB per meter, right? So the sound intensity level or the sound pressure level will decrease linearly with space, and this will be the slope, this will be the rate of change, this A here. So the key thing here is the dB per meter, okay, rather than Nepers per meter. That's what everyone goes on to. The words here aren't really important. That's what's important, whether it's Nepers or dB. So here is this is a famous graph. Oh, I can't get it all on the screen. Okay, so let's start off with the caption. I'll scroll up. So many people have used this graph over the decades. I've used it at least twice. So often, when you want to be able to approximately calculate the attenuation of sound, you can just go on this graph here and pick out an approximate value based on the humidity, the relative humidity, 0%, 10%, 100%. And you can roughly interpolate if you want. So that gets a lot of people by. If you want more precise, if you want a formula for these, we're going to see how there are formulas for this, physical-based formulas. Not just some kind of curve fit where you just dial up different types of curves and see which works. So we have a physical model with adjustable parameters that are then chosen to fit the data. And it fits the data so well that most people consider these curves here to be either theory or data. It doesn't matter. Okay, so it fits really well. This is work done by Bass in roughly the 1970s, early 1970s, I think. Maybe, I didn't think it was early 1970s. This is part of his PhD dissertation. Okay. Now the first thing you want to notice here, okay? Oh, it's log-log. First thing you want to notice. There's a lot of broad ranges here, both in frequency and in the absorption. They're called the absorption coefficient. Yeah. Again, this is the important thing. Okay. So that's the first thing you want to notice, that it's log-log. The next thing I think is to forget humidity. No, I'm sorry. The next thing to notice is, here's the classical absorption coefficient. So you remember, that's the thermal viscous. That includes just the losses due to thermal conduction and viscosity, the thermal viscous losses, right? And the relaxation time there is very short. So this is we're in the low frequency limit here, which means the absorption coefficient is proportional to omega squared. Remember that thing that keeps emerging? So if you look on a log-log plot, what's that going to translate to? Something increasing as omega squares. It'll be linear on a log-log plot, and furthermore, the slope will be what? If absorption is proportional to omega squared, or f squared, you'll notice this is the actual frequency, even though when we do theory, it's always in terms of omega, because we don't want to carry around factors of 2 pi, right? But this is the actual frequency. So it should be a slope too, and you can easily see that here. If you look, for example, I think you can, yeah, if you look here, you'll see that for 2 decades here, it's increased, the coefficient increases 1, 2, 3, 4 decades there. So this is slope 2, as it should be. A log-log plot turns any power law into a straight line, with whatever slope depending upon the coefficients, the powers. Okay, so the amazing thing here is that at high frequency, everything, it's dominated by thermoviscous losses, the attenuation. However, that frequency, you need to note this, is way up there. It's megahertz or 1/10 of a megahertz. It's way up there. So normally, where most of us live, down around here, there is a serious extra absorption mechanisms beyond the thermal that just completely dominate. Unless you start to get up in this region here, it completely dominate here. For example, this is 10 hertz and 100 hertz. So, what is responsible for these? For this additional attenuation here beyond the thermoviscous attenuation? Well, it's molecular thermal relaxations. Okay, so this is where you got to deal with molecules that behave quantum mechanically, of course. And when a sound wave comes by, when it's hotter, compression is hotter, their energy will go into the internal degrees of freedom of the molecule, as we discussed. But there's some time that's required. If time is very short, or if the acoustic wave has such a great frequency that there's no time for the energy to get in there, then there's essentially no absorption due to the internal molecular motion. But if you're in between those two regimes, you're going to get losses due to that phase lag, the fact that it takes time for energy to go in there, as we've discussed. So these other curves here are, this, as I said, this is a percentage, the relative humidity. Okay, let's look first at the 0%. So here's no water vapor. This presumably becomes a straight line of, you'll notice here there's this characteristic structure where there's what we'll call a knee. There's a knee here, right? This is knee, like knee. So sometimes people call something like this. There's this kind of knee here. And you'll notice that if you look at these at higher humidity, it appears to be parallel. They are parallel. We will prove that, okay? So there's this, and presumably, like I said, the 0% humidity will extend down here with the same slope 2 as that one. We'll explain this knee in a moment, but for right now, I just want to point out that KFCS tells us that this knee right here is due to CO2, the molecular thermal relaxation of CO2 with N2 as a catalyst. Okay, they tell us that. It's somehow been identified that that's what's responsible for this very dramatic knee here. I mean, and you can see that we're talking about, look at this, 1, 2, 3 orders of magnitude at 100 hertz, 3 orders of magnitude. That factor of 1,000 greater than the thermal viscous losses. So this is huge. It's everything here. Okay. So they say that it's due to this relatively small amounts of CO2 with N2 as a catalyst. Now, what about when we start to have, that's dry air, okay? What about wet air? Well, what happens for wet air is, there KFCS tells us that the H2O molecules with a strong dipole moment are acting as catalysts for vibrational modes of N2 and O2. Remember those vibrational modes that we often neglect in the heat capacity because they're, I told you the frequency is so high that you're getting close to dissociating? You have to go to such a high temperature to get beyond the ground state of the vibrational modes that you're getting close to dissociation. Well, they play a role here. Okay? And we're told that both N2 and O2 are operating here. In fact, one is N2 and one is O2. I don't know which is which. I don't know if they tell us, and I don't know if it really matters for us. But you'll see here the 0%, the 10%. Oh, you got to be careful here. You got to make sure you follow the curve and don't jump to another curve here. So here's the 10% relative humidity. You can see that there's a knee there, right? A transition between two regions of slope 2. There's a knee, and then here's another knee. One of those is H2O acting as a catalyst for diatomic nitrogen, and the other one is the same with diatomic oxygen. Okay? Now you'll notice that as you go from 10% to 100%, you've got more H2O in there. What's going to happen to the relaxation times? There is a characteristic relaxation time for the 10% here. If you go right in the middle, roughly in the middle of the knee here, and you read off that frequency and convert it to omega and take 1 over that, that's going to be roughly the relaxation time. Remember that? Don't forget the factor of 2 pi floating around here because we're dealing with the actual frequency, not the angular frequency. So we've got a relaxation time here. We've got another relaxation time. So let's see, here's the 10% goes like, here's the other knee for the 10%, right? So right around here at about 10 kilohertz, multiply that by 2 pi, take the reciprocal, we got this other relaxation time. As we add more water, what's going to happen to those relaxation times? We've got more catalysts in there. What's going to happen? The energy goes in quicker, right? So the relaxation time goes down, the relaxation frequency goes up. These two knees here will be pushed that way. And sure enough, if you look at this, let's see if we can get this on here. This first knee is going to become this knee for 100% relative humidity. And this knee becomes, see this knee right here? There's a knee right there. They get pushed that way because we're the relaxation time is being lowered because we got more catalyst in there. Now, what KFCS don't talk about here is what happened to this? Remember this? This is, there's no water. This is CO2. Where, what was it again? I always, with nitrogen and not oxygen? I don't know. But that's due to CO2, right? What do you think happened to this? Well, what's going to happen to the knee? Well, there's really only one thing that can happen to it. Because we've got water vapor in there, it's probably going to serve as a they don't tell us. KFCS doesn't tell us. Hank probably tells us. His first name was Hank. He probably tells us, but I haven't looked in the paper. There's probably a number of papers on this. But it's reasonable to think here that we've got water. It's going to act as a catalyst. It's going to push this knee up here, right? And so what's going to happen to it? Well, I'm going to try to show you, and I think I finally understand this. It took only, I don't know how many years. It's going to get swallowed up in the thermal. It's going to get pushed so high here, I think, that it's way over here, and it's just, you can't see it because the losses are being dominated by the thermoviscous losses. So I'm going to try to prove that. Well, I'm going to show you that could be what's happening here mathematically. We're going to see that in a minute. Okay. Right. All right. So now we're here. We need to understand this pretty clear signature of a molecular thermal relaxation here. This knee, where it goes from slope 2 and then transitions to slope 2 like that. So to understand this, you want to note that we've got two, we're just going to focus on one molecular thermal relaxation. Okay, the more they just add together. Remember, the total absorption coefficient is the sum of the individual absorption coefficients. So we've got this is due to the molecular thermal relaxation. This is just the simple classical, proportional to the square of the frequency, where we know what that is. We know what B2 is. What this is, and if you look back at our example of carbon dioxide, you'll see we had something similar. I think we actually had, it was to the first power here. But that's because we were looking at A over K, or we were looking at alpha over K, or alpha lambda, essentially the same thing. We were looking at maybe this or this. These differ by a factor of 2 pi. This is a dimensionless absorption coefficient. So if you look back, for the carbon dioxide, we dealt with the dimensional value. This has dimensions here. So that introduces another frequency. So this is what we get. So you'll see that from the carbon dioxide, but you have to recognize that we're now not dealing with a dimensionless one. We're dealing with a dimensional absorption coefficient. So this is the basic form. There's some coefficient here that, probably would be really hard to calculate from first principles, so you can treat it as a fit parameter. And then we have some relaxation time. That's probably also hard to calculate. They probably have computer simulations that do this. I don't know. And chemists probably get involved in this, right? So anyway, there's the relaxation. This is the relaxation time. So here's the basic analytics here is that this is the molecular thermal relaxation. This is the thermal viscous losses. Okay. And I just want to point this out to you. This is a relaxation process, but it's in the low frequency limit. This is not necessarily low frequency. This is the general case. If you take this and look at the low frequency limit, what do you get? Low frequency compared to the relaxation frequency. This goes away, and you get something proportional to f squared, which is precisely that. So as far as form goes, this is a special case of this in the low frequency limit, which we know is the case for the thermal viscous losses. All right, so what's the connection between this? How do we get from here to this characteristic knee in the graph? Well, that's not difficult to see here. In fact, I don't even think KFCS points this out, but I think it's good. We should check this. So this is what I just said before. These B's are positive. Okay, and remember the relaxation frequency is not 1 over the relaxation time. It's 1 over 2 pi times the relaxation time. Okay, I've said that enough. I'm not going to say it anymore. Okay, I'll try not to. So to understand what's going on here, let's look at our form. Let's look at it in the limits. This is often what people do, and we've done it a lot in this class. Let's look in the high frequency limit first, I think. So by high frequency here, we mean f much greater than f naught. If f is much greater than f naught, these f's cancel. We just get a constant plus b2f squared. And if you go high enough in frequency, eventually this term will dominate this. We just have a constant here, right? If you go high enough in frequency, this term will eventually dominate that term. And now we just get what? This. We're on here, okay? When we're at frequencies much greater than here. Remember, this is logarithmic here. So This is not twice the frequency. It's a lot more than twice the frequency, okay? This is logarithmic. So we're up here. That confirms this part of the curve. Now let's go to low frequency. If we look at low frequency here, I guess I can just argue this from here. If we look at low frequency, now as I was just talking, much less, this is similar to thermoviscous, then this goes away, and now it's again going to be proportional to f squared, but we've got this additional constant here, b1 over f naught squared. So let's go to the math on this. So we end up with this, okay, where this is a constant. And now, on a log-log plot, we take the logarithm of this. The log of the products is the sum of the logs, right? So I'm going to put this, I put this first for some reason. I get the log of f squared, which is 2 times the log of f. There's our slope 2, thermoviscous slope, well, there's our slope 2. And then now you can see this is just a, this is a constant, isn't it? So what that means is, if we look at the plot of the log of A versus the log of F, we're going to have a straight line of slope 2, but it's lifted from the thermoviscous doesn't have this here. Excuse me, the thermoviscous has that. If you just had, if you set B1 equal to 0, right, if we just had the thermoviscous, you would have this, right? So in the presence of the thermoviscous and this relaxation process, we get this, we lift, the curve gets lifted. It has the same slope, as the thermoviscous too, but it gets lifted by that amount. So that accounts for why we see this here. We got the high frequency limit, the low frequency limit, and it has to smoothly connect, and it's not going to do anything. It's not, this is simple math here, right? The physics behind it is very complicated. It's taken us a number of lectures to get to this point. But the mathematics behind it is quite simple. So it's just going to have this simple, you can't have any maxes and mins. It's going to have this simple knee structure. Okay. So it's displaced the lower well below the relaxation frequency. The curve is going to have the same slope, so it's displaced parallel relative to the classical line and upward, as you can see. Now, I just want to point out, I don't know, this is no big deal, but here's what we just showed that we get this. If you look at the individual contributions, clearly in the high frequency limit here, the molecular thermal relaxation is not contributing. And what it's doing is, it's very easy to see, is it looks something like this. If we only had the molecular thermal relaxation, here would be what the log of A versus the log of F looks like. So there's negligible contribution here. And here, there is a gap there. It's relatively small because this is on a log scale. But this is the sum of this and that. But remember, it's on a log scale, so it's not going to be, this is not a linear scale. So that's why I drew it as smaller there. Okay, so this is what happens for the classical absorption coefficient, thermoviscous losses, which have a short relaxation time, plus 1 molecular thermal relaxation. If you have 2, you just add the other one in, and we'll see an explicit. We'll see this explicitly when we get to water, which is what we're going to do next. So, but you would just add another one on here. That's what we're going to do for water. Okay, so that's all I have to say for air, I think. Let me see if I'm missing anything here. Oh, sorry. Okay, it's not in the notes, but it's going to be edited in there. I want to point something out to you. This is the thing that I finally realized regarding this carbon dioxide, when 0% humidity, where does that knee go when you add a little bit of, you add 1% water vapor, it's gone. And the natural thing to think is it's gotten swallowed up, that this is gone. The relaxation frequency has been pushed so high that it's gotten swallowed up by the thermoviscous losses. Well, to support that, let me point something out to you here. It's really obvious, but it only took me, I don't know how many years to see, here's our basic equation, right? So now I want you to think of this as the CO2 with N2 as a catalyst, or whatever. Okay, this is what this is here. You'll notice when we went through this analysis at low frequency. Now, why are we interested at low frequency? Because once we add a little bit of water vapor, this thing's going to shoot way up, right? So when we look at this at low frequency, whoops, this goes, okay, and we get this. We get this. Now, what if this F naught is pushed so high that this becomes negligible compared to that? Then where are we on the curve? Thermoviscous. So that's what I mean by getting swallowed up. That's probably what's happening here. If you really want to know, I'd go to the literature. Okay, look it up in JASA. And KFCS is pretty good about this. It's the references in the book. One or more references are going to be on this. It's probably in the papers, although I don't know. This stuff is not that old, right? 1970s. And as we're going to, especially now that we get to water, we'll see that it's apparently not completely clear what's going on here. It looks like there's room for more research. So anyway, I think it's reasonable to assume that CO2 relaxation just got pushed up to such high frequency that it's dominated by the thermoviscous losses. Okay, any questions about air? So now, water. Okay. Let's go to water here. So let me just kind of put it look like this and get the curves on there. Now, actually first I should say that for water's polar, right? It's got an electric dipole moment. For nonpolar liquids, apparently molecular thermal relaxation can account for additional losses beyond the thermoviscous, okay? But what about water, which is polar? In this case, because of this dipole action, we're going to have strong molecular forces now. And they cause, the water, now you got tons of water around. And you have all this catalyst, right, for the molecular thermal relaxation. So those times tend to be really short. They get swallowed up in the classical case, okay? But people still observe, as you can see here, the dashed line is the dashed line is the classical absorption. And I want to remind you, the classical absorption is not just the thermoviscous losses. It's the thermoviscous losses assuming zero bulk viscosity. It only has the shear viscosity in there. There's this kind of friction, right, that occurs due to diffusion of momentum that we talked about. Remember the plates? So, but there's also, when you compress something isotropically, there's a kind of friction there too that can occur, and that's the bulk viscosity. So the classical absorption coefficient is assuming zero bulk viscosity. Okay, so it's the dashed line here. So for fresh water, what we see is it's lifted up here, It's a straight line lifted up there. All right? And then for seawater, it's much greater. In fact, it's down here, it's orders of magnitude more than fresh water. And we see the classic 2 relaxation processes, okay? So, what people noticed, however, you might think, oh, there's something, we got to look for some molecular thermal relaxation here. Well, here's the problem. These knees exist at 4 degrees Celsius. And this is the Naval Postgraduate School, right? You all should know what happens at 4 degrees Celsius. Yeah, water is most dense, or densest, whatever you want to say, I don't care. And that means, what does that imply? There's no thermal expansion coefficient. So sound at 4 degrees Celsius is simultaneously adiabatic. Adiabatic and isothermal mean the same thing. Because when you compress it, the temperature doesn't go up. As long as you don't compress it too much. For sound, linear sound, there's slight compressions and expansions. So, what happens to a molecular thermal relaxation process at 4 degrees Celsius? It's not there. It's not operating because there's no heat. The temperature has to go up to put energy into and then go down to get energy out of these excitations. The temperature is staying the same in the sound wave. These persist at 4 degrees Celsius. So something else is going on. And I don't know the history of this. It must have been really interesting, okay? And I don't know what role Hank played in this, and I never asked him because I didn't know at the time. He was the chairman of the previous university I was at, and I didn't know any of this then. And it really upsets me because I'm sure there's a lot of interesting history here. Anecdotal kind of stuff that you probably can't find written down anywhere. So here's what was discovered. Okay? Now, first of all, before we get into the seawater, we better look at the freshwater first. Okay? So, it doesn't take a genius to see that we can mathematically account for this by just simply lifting up our classical thermal absorption coefficient, just increasing it, lift this curve up. Okay? How can we do that? Well, you remember we set the bulk. You remember that the absorption coefficient for thermal viscous losses is proportional to, it's got some constants here, it's proportional to, I think, 4/3. This is the shear viscosity. I think we just called it eta. I think. Yeah, there we go. So, and the classical case has this equal to 0, right? So you can see that what the data suggest here is that one way of looking at it is just we now have a non-zero value of the bulk viscosity. So we can account for it that way. Now that's just mathematical, right? It's just a mathematical way of doing it. But you can fit the data here. And again, people think of these curves here as theory or data. They're so close, there's no distinction. That's how far this has come along, okay? So we think of this as just an eta, and an A to B, a bulk viscosity. To fit it, it turns out it's not a small effect. You have to assume, to fit the data here for fresh water, that the bulk viscosity is 3 times the shear viscosity. All right? So it's not a small effect. So there must be some physics behind that, obviously. So what is it? Well, I don't know if it's known. I'll tell you what KFCS tell us. And the way the book states it is, hasn't been settled. Now, maybe since this edition of the book in 2000, maybe it's been settled, I don't know. But it's very exciting, I think, from a research point of view. Here's the idea. Well, water has, this is the hypothesis, okay? Water has 2 different types of structures. Okay, that you can physically identify 2 types of structures. And these 2 structures have different energy states. So when you pressurize water, it tends to go in one state. okay, into the higher energy state. And when you depressurize, when you lower the pressure, it tends to go into this other state. What these two states are, we aren't told, and I don't know if it is known. I don't know. So here's the point here. We've got these two different states with different energies for water, just due to their, you know, the orientations and locations of these dipole moments, right? When a sound wave comes by and it's higher pressure, and it has nothing to do with temperature here. Well, nothing directly to do with temperature. So this sound wave comes by, there's a compression. The water tends to go, on the average, into this higher energy state, this more compact higher energy state, right? And if there's a time, you know there's going to be a time delay there, right? Okay, we're done. That's a relaxation process. So that's the idea here of how you get that. This is going to be what's now called a, I don't know if they have a name for it, but it's a kind of structural relaxation process. It's not thermal. It's a molecular relaxation process. I don't know. It's not for a molecule, though, is it? It's a collective effect. So maybe we'll just stick with structural relaxation. It's a kind of structural relaxation time there. So once we posit, or once we hypothesize that, then okay, that can be tested. And what are the results of those tests? I don't know. If this is really going on, if there is this really a second state of water here, it should occur in other experiments, not having to do anything with relaxation, right? But I don't know what's up. The textbook doesn't give us any information about that. Yeah.
So like now how the molecule itself works.
Yeah, no, it's the structure.
Bonding, like the way they bond.
Right. So in a very rough way, you want to think of a crystal, two types of crystalline structures. You know how crystal, that's a solid. We're dealing with a liquid here, which is different. But in a crystal where the molecules are all frozen, you know that you can have different crystalline structures. So here they're sliding around, it's like a molecule, but they're these two rough approximate structures. And it's probably, if it really exists, it's probably very vague, you know. You might not be able to see it by eye, but there's some preference for some kind of regular structure. And it's not going to be regular. Liquids are moving all over the place. But on the average, there's some kind of preference for one structure over another structure. And they're distinguished by pressure. If you pressurize, if you've got it in there, and you've got these two states, and you pressurize, the higher energy state, the more compact state, becomes a little bit more preferable. That's all it takes. You got a relaxation process there. Because it's going to take time for the molecules to do that. So it's a great idea, right? And I've never looked it up. I don't know if that's been confirmed or what's going on here, but it's really interesting. If anybody gets interested in this, please contact me, okay? Okay, so that's the latest, according to KFCS, the year 2000, of our understanding of why the fresh water is lifted up here. Okay, one possibility. So what about seawater? So seawater now has this as its base. Our thermoviscous is now going up to here. And at high frequency, it's going to go to the thermoviscous, and now we're including the bulk viscosity. Okay, so we see that up there. Presumably that just keeps going like that. Okay, and then we see two relaxation processes. Remember, these are not thermal. They persist at 4 degrees Celsius. So, whoops, sorry. So what are they? Well, they've been discovered to be, they are obviously relaxation processes because we got a knee here. I tend to look at this from going from high frequency to low frequency. Okay, so let's look at the first one here. This has been found to be due to magnesium sulfate. Did anybody know that there's magnesium sulfate in the ocean? Okay, so I don't know how much there is. I don't think it's a lot. Okay, but it doesn't take a lot. Okay, so what's happening here is, so the first transition as we decrease, it's usually easier, I think, to look at going to decreasing frequency, but anyway, it doesn't matter, your choice. So there are magnesium sulfate atoms in there, and then there's dissociate. There's an equilibrium. So at some temperature T and some depth, it's going to be depth dependent, okay? There's going to be a certain fraction of the molecules and the ions here, right? Now, what happens when a sound wave comes by? Well, my guess is, well, it's got to go one way or the other, and the natural guess is when the pressure goes up, you get some of these combined. This is always continually changing, right? Molecules are dissociating, the ions are associating. I don't know they're combining, okay? So it's always this continual process, and there's an equilibrium. When the pressure goes up a little bit, my guess is, and we're not told, my guess is the fraction of MGS, the molecules, is a little bit greater. It's reasonable to think that, okay? So that combination takes time. What do we have? It's called a relaxation process. So that's been identified as the first knee as you go from high frequency to low frequency. And you'll notice it doesn't depend directly upon the temperature here of the sound wave. It depends upon the equilibrium temperature, because that's going to alter the relative amounts of these ions clearly. At greater temperature, you're going to have more ions. That's going to increase and that's going to decrease. But as far as the actual process goes, at the acoustic frequency, the temperature doesn't play a direct role there. So that's why it persists at 4 degrees. It occurs at 4 degrees Celsius, in addition to other temperatures. The next one, as you're going down, is boric acid. Boric acid? So there is apparently boric acid in the ocean. I'm sure there's all kinds of stuff in there. And a lot of it we're probably responsible for. But anyway, here's the magnesium sulfate. This knee right here is boric acid. And the remarkable thing here is that boric acid is present in 4 parts per million, roughly. Roughly 1 molecule of every 250,000 is boric acid. And boric acid has the effect, as you're going down in frequency here, if the boric acid wasn't there, this line would just keep going with slope 2 here. Boric acid is responsible for this, and you can see that it's not an order of magnitude, but it's a factor of, 5 or something like that. It's big, it's not small. It's lifting this up, giving us greater attenuation. It's really remarkable. So how do we combine these two? How do we come up with this curve? How do they come up with this curve? Well, we talked about this. We didn't explicitly look at it with air, but we can look at same idea, air and water. Here we go. The absorption coefficients add. So we have these 2 relaxation processes here with relaxation times. It looks like these have now mysteriously switched their order. It's of course irrelevant. But here's the relaxation time, F1, F2, for these 2 processes. There'll be these positive coefficients here, overall coefficients. So, ultimately you should be able to determine these quantities by independent experiments, not have to deal with sound. You can perhaps ultimately actually derive them from first principles. But I doubt if anyone's been able to do that, but I don't know. But you can also, as you guys well know, you can just treat these as fit parameters, right, fit to the acoustic data. And that's probably what they did to generate these curves. I don't know. Probably treating these as fit parameters. So this curve here, where at high frequency it goes into the thermoviscous with the additional bulk viscosity, with these 2 relaxation processes here, is modeled by this, is physically modeled by these functions here. Now, I just realized an interesting historical question is, what happened before this relaxation theory? How did they probably had data for this. How would they account for it? Well, they try to come up with some fit curves, right? These curves are sufficient. Now that I think about it, these functions here are sufficiently simple that they probably did that. I don't know the history here at all, okay? But often something like this, the data will exist before the theory, but Not necessarily, but it's often the case. And so when experimentalists have data and they have no idea how to do a theory, they're just going to try to fit it, right? So this is these aren't that simple. In fact, this is probably called something. You guys are fit masters. What is this called? It's like Lorentzian? I don't know. No, it's not Lorentzian? I don't know. I thought you guys just fit everything. Okay. Okay, so again, however, you'll note that there's a big difference here, just trying to grab any kind of mathematical function. This is physically based. It's physically based. It's rooted in the relaxation process. So KFCS actually have more on this. For these formulas, you can look at, I think they give formulas for these coefficients here, for these A, B, and C. And these are just going to have to be, you got to find some values. But they have formulas for A, B, and C in terms of depth and salinity and, so pressure, depth is pressure, and temperature. So I think they have that. So that's the idea of how you can use, calculate absorption coefficient. So we'll look at an example of that in homework, where we calculate some actual values from this with numerical values in here. So finally, I just want to point out one more. I always forget this. This is very minor, but it's in the book, and I put it in here. I should probably take this out. So here's what's happening when we have two relaxations. Remember one relaxation process? We had this. I did a sketch of this, right? So two is just going to look like that. So I don't know if this is really worth it. And I don't really know why they put it in the book. But it's not. I don't think it's really necessary. But it's just a slight. It's just looking at the individual contributions. That's all. The last thing I want to say is that this is amazing here. If we think of, like we were talking about before, if we think of boric acid as a contaminant, okay? So you're in the ocean, and you have this 1 part in 250, 4 parts per million boric acid. And you're looking at sound down here around 1 kilohertz. You get much greater attenuation than what you would predict when there's no boric acid there. All it's taking is 1 part in 250,000 to cause this big effect here in the attenuation, something that's easily measured, very dramatic. So again, as I mentioned to you before, that's a warning that just because there's a small amount of a contaminant doesn't mean that there can't be a big effect. Philosophically, it was thought hundreds of years ago and before then, it was thought that a small cause would give rise to a small effect. That was sort of a favorite idea that people had. Well, that's fallen by the wayside. I mean, look at a ball on top of a hill, right? If I impart a little bit of momentum to that ball, it can just run away, right? So unstable systems, a small effect can have a small cause can have a huge effect. This cause and effect thing here. And we're seeing, so that's sort of a dynamical or stability kind of thing. And it's well known. There's a lot of nonlinear dynamics, examples of that, where, and the classic one, I don't know if I've ever told you guys this, but in the 90s, there was this big, roughly the 90s, there was a big, regarding the climate of our planet, there was this big worry that as the climate warmed up, that some of these giant conveyor belts that keep Europe warmer than it should be, because there's these ocean conveyor belts, steady flow, that there would be an instability there and they would shut off. So Europe would just freeze. And it can happen over a period, I don't remember, but it's geologically short time. I think like decades. It can happen. This kind of thing is predicted to happen. So it was a great thing for people like me who do nonlinear dynamics to point. There's a demonstration I do where it's just 2 coupled oscillators. But if you if the amplitude becomes too high, becomes a little too nonlinear, the mode that you're looking, it's really simple. Oops. So you can make it, it's two coupled pendulums like this. So these are strings and a mass. We're in a gravitational field here. Okay? And I actually published a paper on this with some undergraduate students. So there's two modes here. This mode, two normal modes. This one, and what's the other one? This one. In phase and out of phase. Right? So, and that's well known on the linear level, and some of you have done this in the 3000 level. You've done normal mode analysis, linear normal mode analysis. Well, what happens here is if you look at larger amplitudes, the out of frequency mode remains stable. This mode, there is an angle there lurking, okay? And you don't see it directly, but as you increase the amplitude, you slowly increase the amplitude. Eventually, when you go beyond this angle there, it becomes unstable. And it starts to go like, energy goes into both modes. It's an instability. It's like a ball on top of a hill, except it's not obvious. So that's an example of where a small cause can have a huge effect, and instability. But here we're seeing it, it's not an instability. It's just in the dynamics of this, in this molecular relaxation process here, that a real small cause, a little bit of boric acid, can have a big effect. Okay, this lecture was supposed to be shorter, but I still managed to go over. Anybody have any quick questions? All right, so